Well, good morning, dear. So, welcome back. So, this is our lecture number 14, and I will try to conclude about linear regression model in this lecture. Uh, so far, if you see, there is a sequence of development about the various aspects of the linear regression model across all these lectures. Okay, here today I am going to talk about various applications of linear regression model. Okay, believe me, linear regression model is simple, very elegant model, and industry first use it. Okay, and widely they use it in all kind of predictions. Okay, um, let it be weather forecasting. Okay, because you have data. Okay, and based on that, simply if you want simple prediction, then you can use linear regression model. Then various business sales forecasting. For example, you have data about what happened earlier about a product's sale, and if you have authentic data through regression analysis, you can predict that what is going to happen in the future regarding the sales of this particular product. Okay, take the example of ACs. AC is a product which whose sale is seasonal, right? During summer, it reaches to the peak. During winter, there is a plateau. All kind of things. If you have data earlier, then based on that, you can predict in next summer how many you are going to sell. All kind of thing. Then also risk prediction. Okay, suppose you are trying to maintain some inventory, assuming that the sales will be very good in the coming months. Okay, for that you have to have data for earlier such events, and then from there you can predict how much risk is involved in putting money in maintaining the inventory or buying a company. It could be anything. Okay, and in all those cases, your linear regression model can help you. Then stock market prediction is another area where you can use many sophisticated machine learning tools which you will study, and at a first hand you can also use a linear regression model. For example, you would like to spend some money in a particular company, so you can gather data of that company, previous data, and make a kind of regression model to see that whether that particular company is market value will increase or not. Okay, then instrument calibration. This is another wide area of application for linear regression model. And as you know, many instrument, almost all instrument and sensors, they need calibration before use. Okay, I can illustrate with a small example of weighing machine. Weighing machine, if you go to the market and you buy some product, they put it on the weighing machine, and then the pointer, of course they are digital also, but pointer moves. Okay, let us try to understand with that example how it works. Okay, say, so this is 0 kg, and then I 5, 10, 15, 20, 25, 30, 35, like that. Okay, and there is a pointer here. Okay, what is actually moving the moment, say you have a pan over here, so you are putting some product. Okay, and you see the pointer is moving in this direction. Okay, now, and we are believing whatever pointer is pointing, that's the weight. But before that, you need to calibrate it. Calibration means it has a, the way it works, the pointer is loaded through a spring. Actually, when you are putting some weight, okay, the spring elongates, spring is undergoing some force on it. Okay, and this is mg. So spring is undergoing some kind of deflection, okay, says delta, then applied force F equal to mg equal to k is the stiffness constant of the spring, and delta is the elongation of the spring. Okay, so there is a relation between force and elongation of the spring for a particular stiffness constant of the spring, or the particular spring. So that is force is mg, and then you put some, when calibrating you put some weight, say 5 kg, and see where y is your deflection of the spring and x is your weight, for example, and where the y moves. So this is 5 kg, and then you level that this is 5 kg. Then you put some weight 10 kg and put it value of 10, 15, 20, like that. Okay, and then you draw a regression line. So and then you just graduate, make some graduation, okay, so that you can measure the intermediate weights also, right? Okay, so during calibration, put known weight and see where the pointer is moving, and then you gradually calibrate. Our fundamental assumption is the behavior of this regression line is linear. If it is not linear, then of course you cannot use it. Okay, so linear zone we normally, that's why use. So in between 0 and 5, you have not calibrated. You are believing your regression to give an answer, say 5 point something. So it will, you will get y value also, some weight, unknown weight you put, and the indicator is moving, say 5.2. So you predict, okay, the weight is 5.2 kg, like that. Okay, so once you calibrate with own using regression, and then use that regression model to predict for unknown weight. Okay, so this is another simple example called calibration, which actually are widely used. The regression model helps them. Okay. Other applications are, say you are developing some kind of app, say fitness app. Okay, everybody nowadays in mobile have some kind of fitness app. If you undertake morning walk, so it tells you how many steps you have walked, and then how many calories you have burned, then what is the distance you have covered, how much time you have walked, all kind of information they give. How they are giving it? They are only collecting information from sensor, one sensor, for example, accelerometer, okay, and through regression from accelerometer sensor, which is actually counting your step or telling you the position, measuring your position, and then you have calibrated earlier that, okay, if this is the position, then this much of time is elapsed, this is the position, and then this much of calories burned, like that. Okay, all kind of things. So it could be multiple regression analysis, it could be single variable regression. But what I am trying to make a point here, you are using, perhaps designing the app, perhaps using plug and play, but behind the scene there is an algorithm which is using linear, might be using linear regression, not might be, actually they use linear regression because it is simple and it is elegant. So these are some of the applications which linear regression model has. Apart from that, I try to introduce the various concepts of machine learning using this linear regression model. Let us try to recapitulate or summarize what we have done so far. We have some level data which we are using for training. Training means doing regression analysis and making a model. Okay, and there are various types of tools available. First we used the normal equation model, and then normal equation when there are large number of variables. If there is single variable, it was easy. Okay, when multiple variables, then we had to formulate it in the form of a matrix. Okay, so normal equation in the form of matrix we discussed, and in that context we realized that it is very elegant, very easy, but there was a matrix inversion, and then that was a problem, and then we take you to the iterative mode of regression analysis. Okay, that is gradient descent algorithm, a bunch of gradient descent algorithm we discussed. Okay, it's an algorithmic way, and each time you have seen, first you need to have a cost function, then you need to derive that make a derivative of the cost function with respect to the parameters, okay, with which you are going to design the predictor. And either you are determining the parameter using equations in case of normal equation tools, or converging the parameters, means evaluating in an algorithmic way those parameters. You also design the predictor. So then we discussed about various different kinds of fitting, okay, overfitting, concept of underfitting, overfitting, best fitting, okay, and in that context we just introduce you what is bias. Okay, bias means high bias means you are using fewer number of parameters, okay, and it will have poor generalization and prediction will be poor. On the contrary, in overfitting problem, you are using more than necessary number of parameters, which is also bad. We call high variance. Okay, so high bias is bad, high variance is bad, and then we compromise that, okay, we will take best of both the world. So optimum bias, optimum variance, and then that will give you best fit. And we also try to understand that using a regularizer how the best fitting can be accomplished. Okay, and you have seen that in regularization you have this kind of parameter 1 minus alpha lambda by m, and that is actually what is regularizer is doing. For a constant learning rate for a given sample, this if you have higher lambda, that means you are shrinking this parameter too much. That means you are making the hypothesis too simple, and then there will be high bias and bad prediction. On the contrary, if this is too low, and then you are shrinking this parameter very small value, and then again it's bad. It is a kind of high variance, overfitting problem may occur. So very judiciously for a given alpha and m, judiciously lambda has to be determined, okay, and there is no easy way, but there are some standard method. Method is that you use some by empirical methods, use some reasonably high lambda 1000 or in that range, and then see try to tune that parameter, okay, and then till you get a best fitting. That means best prediction means your predicted for unknown samples, predicted error should be less, okay. Till then you can tune this lambda. So you see alpha, lambda, we are calling them hyperparameter. Why? Because they are controlling the parameter, okay. They are controlling W, okay. There some is controlling W, that is lambda. Some is controlling the how much increment will be there or decrement will be there in the value of parameter. That's why they are called hyperparameters. So you are introduced with that also. And then we discussed about pre-processing of features, that is feature scaling, some techniques, and why it is needed we discussed. And also we told that in case of normal form of equation, you don't need feature scaling because it's a matrix, and then matrix manipulation without feature scaling can be done effectively. And then we discussed another very good algorithm which not only can predict the linear trend of the data, but dynamically non-linear trend of the data, okay, can also be tackled with also be tackled with a algorithm which we called locally weighted regression algorithm. Okay, so all these tools you have studies, and their use slowly when you will practice them, you will come to know each has some advantage, some disadvantage, some specific area of their applications. Okay, and after that we also introduced you that what is the probabilistic or statistical interpretation of linear regression model. And it turns out that statistical interpretation of the linear regression model is very simple, and they are converging to the same cost function which we have designed using the concept of error. So here in purely statistical interpretation model, what we assume, you are getting some error, right? And based on the error you are designing, minimizing the error, you are designing the predictor. Here you are having error, okay, and we are assuming the for random x and y, the error will be exhibiting normal distribution. With this assumption is needed because otherwise I cannot write in a analytical way the function which we are calling maximum likelihood function for the parameter w. You know, x and y, they are random variables, but w is a parameter which is not random variable, which we are trying to determine. And with illustrative examples and figures, I tried to show you that this intention, that is what will be the maximum likelihood of estimate of our parameter, which will give you minimum error. It means for given sample, probability of getting y, that is the actual level, is maximum. Okay, so once we do that, then the probability density function, which is a normal distribution function, we could write, and then we try to maximize that likelihood function of w. And it turns out in the process of maximizing, we got one term minus a term which needed to be minimized, because you are maximizing the function which has two parts, one minus something. So that minus something has to be minimized, and in that process it turns out that this is nothing but exactly the same cost function which we know. So this is purely statistical interpretation of linear regression model. This understanding, this is very, very important, because this model we will use in our further discussion. Exactly the similar model we will use for many further discussions, right? Logistic regression, then GDA and all many. This is very, very important. That's why it is very important to know that you are calculating the maximum likelihood of you are trying to estimate maximum likelihood of the parameter, and in that process you are getting a probability density function, okay, and that is giving you whatever what you desire, okay. So with this, we will conclude our discussion on linear regression model. If you have any question, please come to the discussion forum, and we have every week we have discussion forums, and you can also write to us. And till then, stay safe. Have a nice day. Bye bye.